Hello, calculus students. I hope you are doing well. This is the beginning of the second half of the course, roughly speaking. And for the rest of this semester in Calc 3, we'll be talking about integrals. All right, so as you know, calculus is basically twofold: differentiation on one side, integration on the other. And we are now transitioning from differentiation to integration. All right, so what in the world is an integral? Okay, and that is the main question I would like to answer in this video. What in the world is an integral? From grade 3 to calculus 3. Yes, from grade 3, where you learn how to add and how to sort of look at graphs and how to calculate things like distance traveled, to calculus 3, not only a single variable function course, but a multivariable function course. All right, and so I hope you'll find it important, interesting, and relevant. And what you understand or what you learn in this sort of an independent special video will help you really understand what integrals are. And that will help you for the not only for the rest of this semester, but as you go into more advanced classes where integrals play a main part. All right, so get ready. What in the world is an integral? All right, so first, let me explain that there are two types of mathematics, and these are not normally discussed in any of discussions of mathematics as a whole, but there's a thing called a discrete aspect or discrete mathematical objects and continuous mathematical objects, right? So discrete means we are talking about either a finite number of elements, like 1, 2, 3, or possibly infinite, but countable. And countable means that you can start to count like 1, 2, 3. Okay, so it's called a countable set, right? So those are called discrete. Notice here, if you have a line, 0, 1, 2, and you can even include negative numbers. If you want to, you can do that. And notice here, these are completely apart from each other on the number line, right? So if you only have integers, okay, that is sort of a discrete kind of case. And continuous means something that's an interval, like from A to B. Of course, you have infinitely many real numbers. And the way we describe this is it is more than countable, right? So for instance, if you want to list all the integers, for instance, you can start counting, okay? And there is a way to put the set of all integers in a one-to-one correspondence with the set of these numbers starting at 1, 2, 3, and so on. But there is no such one-to-one correspondence between the countable set like 1, 2, 3, all the way to infinity, even though it's infinite, right? There is no way to put this in one-to-one correspondence with any part of the real line, like an interval or the whole real numbers. So this is uncountable, right? And uncountable basically means that you have all of these points. In between two real numbers, there are always real numbers, in fact, infinitely many of them. All right, and so we can talk about the set of real numbers, infinity. Well, I don't want to put the infinity because it's not a number. When we talk about an epsilon delta proof, right, you know that epsilon is an arbitrarily small positive number, right? So whenever we talk about these things, we are talking about continuity, and the word continuous, as you know, has to do with epsilon and delta. Limits have to do with epsilon and delta. So continuous is what we are doing in calculus, right? We are not studying discrete mathematics, even though that we do offer a class called discrete mathematics. Calculus is definitely the opposite of discrete, and it's continuous. And this is important, okay? This difference will help you really understand and answer this question: what in the world is an integral? All right, so keep that in mind. All right, so I am going to ask you a question from maybe your grade 3 class, right? And maybe I should make this a little longer, okay? All right, so here's a question. If you drive at 60 miles an hour, sounds like an old word problem, right? This is when you used to like word problems, maybe. All right, so let's say you drive for 4 hours at 60 miles an hour. How far did you travel, right? And you probably learned that the distance traveled is rate times time. In other words, you multiply the speed by the number of hours. All right. So in this case, you get 60 times 4 is equal to 240. Now, don't tell your friends and family that you just went to calculus 3 and you learned that 60 times 4 is 240. That's one way to solve the problem. You just multiply, right? But you can look at this as a function, which is a constant function at 60, in the interval from 0 to 4, right? Now, when you're in third grade, you probably didn't do it this way, but the integral from 0 to 4 of 60 dx turns out to be 240, right? So you know that you traveled at 240 miles in 4 hours, if this is indeed your speed, okay? Now, this is your third grade. Okay, this is your calculus 1, whenever you do calculus 1, maybe fourth grade, right? So you can tell that these are different ways of doing this, right? Now, let me change the problem a little bit. What would have happened if you drove at 60 miles an hour for 2 hours, okay? And then 50 miles an hour for 2 hours. Okay, so you may have gotten into a little congestion or something, and so this is 50, right? So you know that this area here is 120, it's 60 times 2, and here it's 50 times 2 and 100. So total, you have 220 miles an hour. You get that? All right, so if the function represents a speed, and if the horizontal axis represents time, then of course you just find what you're seeing right now is, of course, what we call step function. And for step functions, or we call them piecewise linear or piecewise constant functions, it's easy to calculate the distance. And you know that you're really looking at the area under the curve, right? Right. So what happens if this changes more? Okay, so for instance, if it changes, from 60 to 50 to 70 to 40, for instance, I don't know. No, it's 30, right? So if this is 60 and this is 50, and then you were able to go a little faster here, and then you hit 405 and you went down to 30. Okay, so that would be what? This is 1, 2, 3, 4. Every area or every rectangle has the width of 1. So this will be 60, 50 plus 70 plus 30, right? And so you will say that's 210. The point I'm trying to make, and you can see what I'm doing here. I started with the interval of length 4, and then I went to 2 intervals of length 2 and 4 intervals of length 1. This is called the refining or refinements of the partition. All right, and of course, you probably have guessed where I'm going from calculus 3. I mean, from grade 3 to calculus 1. What happens if the speed changes constantly, which is exactly what happens when you drive, right? Probably, well, I mean, you can use your cruise control, I guess, if you like, right? But typically, your speed is changing all the time, okay? And in that case, what you can do is to divide this into either much more much smaller or much narrower intervals, right? And basically, if you calculate the area, the distance traveled is exactly this area. Now, I can write this as an integral, right? But this is really the area. And this is the point I'm trying to make, right? One of the things you have learned is that the definite integral represents the area under the curve if the curve is non-negative or positive, right? In this case. So that is the first way you learned how to what integrals meant or what integrals mean. So you could say the integral represents the area under the curve of a non-negative function. And you do this exactly in this way. You divide the interval into very, very small subintervals and then calculate, right? But what I want you to notice here is you don't even have to have this graph like this, okay? And I'll come back to this in a moment. But you can see the same idea in many, many places if you just open your eyes, right? So, whenever a gym is open, you can go to treadmill. Some of you may have a treadmill at home, which you may never use. I don't know. But if you go to treadmill, most of the treadmills have these little panels in front of you, and it'll keep track of how much you're running or how many calories you're using, right? So let's say you're in this mode of the panel. They're telling you how many calories you're burning, and they'll give you a little graph like this maybe, right? And when you're running hard and fast, you're using more and so on. And so what do they represent? This, and this is of course time, right? Let's say you have spent an hour on a treadmill and these are the calories, or it could be distances, right? Whatever, okay? So what happens is in the first, I don't know, 10 minutes or so, or maybe 5 minutes, right? This is how much calories you burned. And this is how much more you have burned in the second time segment and so on, right? And they have these different segments. All right, so the total area under the curve again, what you're really doing is adding the areas of these rectangles, right? But that would be the total calories burned. When they say calories, that they really mean kilocalories. All right, so that's what what this will tell you, right? Okay, so here's another way to understand this. COVID-19, right? You have probably seen graphs like this, maybe almost daily in the media. The COVID-19 crisis, the new coronavirus crisis, began at the beginning of the year, right? And so the United States, this is the graph from the number of cases in the U.S. For January, there was none, and maybe January 31st. You had February, and then March 22nd, and this is when the lockdown started to begin, started to happen. And you can see the graph. Now, the orange graph is the continuous function, which sort of represents a 7-day average. Okay, and again, this is definitely not continuous because they are taking 7-day average every single day, and every single day is discrete. Okay, but it is easy to connect the dots, especially if you're talking about averages, because that's sort of like linear, right? And so that you can see the continuous function, and you can see all these bars. Okay, so this is for each day. For each day between what December, February, and July or August or whatever, whenever this stops here, this keeps track of, so this is how many new cases. All right, and so what is the integral? Let's say if this is f, and if this is a and b, the integral from a to b of fx dx is basically the sum of all of these numbers of new cases every day added together, right? And this, I think, gives you a very clear understanding of what the integral is. An integral is adding up a bunch of things, okay? Just adding a bunch of things. But what difference now, the difference between a simpler addition and integration is that every single point, okay, now I know it's not true with the COVID because it's not every single point, it's just every single point or every single bar here represents one day, okay? And so days are, again, discrete. You don't have infinitely many days. So there aren't infinitely many numbers or the values or X values here. There aren't infinitely many points. Definitely, it's a finite number of days. But you can almost see the precursor of what an integral looks like. Okay, what you're really seeing is what? Yeah, this is basically the Riemann sum, right? But it's a sum of all new cases. So if what does the function f represent in this case? Yeah, it is a number of new cases per day, right? Per day. So that means it is like the speed or the velocity. This is the number that is increased on this day, and this is the number that the new cases have increased by on this day, and on this day, and on this day. So this is representing something similar to the velocity. And if you integrate the velocity, you get the total distance traveled. This is the total new cases, right? So it is very easy, I think, to if you open your eyes to see illustrations of of the integrals. All right, now I'm going to use this scenario or a metaphor of Lego pieces. All right, so I want you to keep this in mind. Let's say you have a bunch of Lego pieces. All right, so you have 2 Lego pieces here, maybe 3 on the next tower, maybe 4 on the next, maybe 1 on the next, right? And so maybe 4 here, and you may have 6 here, right? So let's say you have a bunch of these Lego pieces, right? Now, why am I talking about Lego pieces? Because the point is that, every single point, let's say here's a point X, and f of X is the number of Lego pieces stacked up at X, right? And then you know what the integral represents, right? Let's say this is A and this is B, A, B, and the height is f of X. If you integrate f of X from A to B, oh, by the way, we can't talk about integrals of these piecewise constant functions, okay? You don't have to find antiderivatives, and that's another a myth, okay? So don't think that you have to have an antiderivative to find the integrals. There are many functions like this one here, or like this one here, where of course there is no antiderivative because function f is not even defined as a exponential or log or whatever functions that you can integrate. Most functions in life are just shown by graphs. They don't have the formula. So the integral doesn't have to depend on the existence of an antiderivative. You can define an integral as basically the sum again, right? So this is the key word in this section of our talk. It's a sum, all right, the total. That's what the integral is. It's a sum of all Lego pieces over here. All right, and what kind of sum is this? I have hinted at this, but what I am illustrating here is all discrete, right? Except here, this, if you assume that the speed is changing constantly at every second or every fraction of a second, every moment, then you would have to go into sort of a discrete case of addition from discrete to continuous way of adding things. How do you add things in a continuous way? See, here you have so many x values. I don't know how many you have here. 1, 2, 3, 4, how many columns, however many columns you have, that's a number of x values. So this turns out to be adding that many number of numbers, right? So it'll be like 2 plus 3 plus 4 plus 1 plus all the way to this last 4. So that's a finite sum, of course. All right, so keep these in mind. And so finally, here's another set of illustrations. This is my last set of illustrations to bring back to our point, the main point, what is an integral, all right? And I think this really is the best way to understand what an integral is. Okay, so suppose you have a stick, right, or rod, right? And let's say this is 4 feet, right? So this is 0, this is 4, okay? And I am going to say that, let's say this rod, or maybe a walking stick or something, is made of a material, some sort of a metal, which weighs 5 pounds per foot. Okay, so this rod is a 4 feet tall, 4 feet long, and every part of this is made of the stuff that's 5 pounds per foot. How much does it weigh? Okay, now you can immediately say, well, of course it's 4 times, well, it's 5 times 4, right? 4 times 5 is okay too. It's 20. And what's the unit? The units are, well, you have pounds per feet times feet. So the feet and feet cancel, right? So this will be 20 pounds, right? You can also think of this, as we did before, as a constant function added together, right? So this is what's happening. This is 4 and this is 5. And at each point, you are adding 5, except this is the value of the function is 5 at every single point, okay? And if you integrate, which you don't because you just multiply, right? I mean, you only have a finite number of, length, finite length, right? It's 4 feet. And so 5 times 4, which is, 5 times, so 5 plus 5 plus 5 plus 5, you can divide this into a foot long pieces, and you have 4 of them. And so that would be 5 times 4, right? What happens then if the first half is made of 5 pounds per foot, and the last part, the second half is 10 pounds per foot. Okay, so this second half is heavier than the first half. And you can see what I'm trying to say is like what I'm giving you is like the density function, except it's not technically density because I'm not using grams or kilograms. Pounds really is not the unit of mass, right? I mean, technically speaking, if you're a physicist, a pound is a unit of force in the American or custom system, and so you should be using something like grams or kilograms or even slugs if you are representing true mass. Okay, so I'm not talking about density technically, but it is sort of like that. You know, we are trying to tell you, or we're trying to find out how heavy the rod or the stick is. All right, so here you can see again, this is 5 times 2 because the first half has the length 2 feet, and then you have 10 times 2. So that would be 30 pounds altogether. And for this one, of course, you can tell this will be 5 here and 10 here. And, you know, that's the area under the curve is that, right? Now, what happens if every single point is has a different density or different number of pounds per foot? Okay, so Fx is um, what we call density. I know it's not quite the density, but it is the number of pounds per foot. Okay, so and x changes at every single point. Okay, in other words, this rod or stick is made of different material every single point. Maybe lighter here, heavier here, maybe lighter here, and you're trying to calculate the weight of this. Well, in this case, the weight can be and has to be described because it changes at every moment or every point x on this stick. It cannot be defined as a finite sum. Okay, you have infinitely many summons, and so it's the integral of fx dx from 0 to 4. Right, so that's one way to write that. And the graph is going to look something like this from 0 to 4, right? It's heavier here, lighter here, heavier here, really heavy here. Okay, so what in the world is an integral, right? So you went from discrete, this is a discrete sum, this is a discrete sum, and this is continuous. And what you're doing is you're adding the value fx at every single point x in a sense. All right, so what I want you to take away from this, this is a number one takeaway. Integration is a continuous version of addition. I will be referring to this over and over, not only in this upcoming chapter, but the next one. Okay, and I will say, what is integration? And your answer should be it's continuous sum or continuous addition, or it's a continuous version of addition. All right, so and what you're given is when fx is given at every point x in the domain. All right, so in this case, you had, you know, for each x here, you are given the value f of x. Just like here too. I mean, at each point here, you know, the value is defined. Like in this case, for each x, the value happens to be 5. So it was easier. It's a discrete case. Second case too, it was easy because it's also discrete with just 2 things added together, right? But in the last one, you couldn't do that because you have infinitely many numbers, but you are still, in a sense, adding I mean, the way the Riemann thought about this, you are adding a bunch of tiny, tiny pieces of the stick. In other words, you take the stick and slice them into really, really, really small pieces. Okay, and each piece, of course, has a weight. You add them all up, and you get a Riemann sum. And of course, if you keep refining this, you get to some limiting value, and that is defined as the integral, right? So integration is continuous addition. That's what I want you to remember. Integration is a continuous version of addition. It is a continuous sum, quote unquote, even though there is no such a thing as a continuous sum. It is a continuous version of adding various numbers, and the things you're adding are fx, and you have infinitely many of them because at each point x, each real number x, fx is defined. Right. Now, this is an interesting and important thing because I am not really describing this as area under the curve, right? Even though I do have the curve and the graphs defined. I'm primarily concerned about, I'm primarily describing the integral as a continuous sum. And that's, I think, is the best way to think about integrals going forward, okay? Because see, the thing is, I'm going to keep adding dimensions. What we have now is a one-dimensional function. And as you know, we are about to go into two-dimensional and three-dimensional functions. In three dimensionals, if f has x, y, and z as its independent variables, I can't even graph this thing because the value will be in the fourth dimension, right? And so what does it mean when I take the integral? This would be a triple integral of f of x, y, z. See, I can't describe this as the area under the curve or area under over a region. But this thing, the idea of density and the total weight, that idea will still make sense even when we talk about three-dimensional objects and integrating over three-dimensional space. All right, so that's what I would like you to remember. All right, so let's now move to a sort of a careful definition of an integral. Okay, so given fx defined for all x in this interval, usually we use a closed interval here. All right, so you have this a, b, and you have this. I'm going to try to make this a little bigger because I think it's important for you to see this. All right, and so once I have this definition or have the function defined, then we can start the definition of a definite integral by what's the first step? The very first step is to define what is known as a partition. All right, so number one, define the partition. Okay, what is a partition? A partition is basically a finite set of numbers along the x-axis. All right, so we're going to let x naught be the starting point. This is x naught, right? And then you have x1, x2, x3, all in ascending order, and goes up to xn, which is b. All right, and we insist that xi is less than xi plus 1. All right, so basically you have x1, and we don't even have to make them of the same length. I'm just defining this in the most general case, and then the last one is x sub n. All right, so now we have n subintervals of this. Okay, so this is called a partition. All right, and then we let delta xi to be, all right, so delta xi is delta xi minus xi minus 1. All right, so this is the, what is that? This is the width or the size of the ith subinterval. I hope this makes sense, right? So let's pick, see here, 1, 2, 3. Let's pick this one here, okay? So here is, this is my fourth subinterval, right? And the length of the fourth subinterval is, of course, x4 minus x3, right? Okay, that's what we're talking about here. And so each subinterval has the length delta of xi. All right, and with that, the next thing we do is, see, here's what we would like to do. We would like to pick some point in each subinterval, like I'm picking the fourth subinterval, and I'm going to pick a point, a random point, okay? Any point in the subinterval. It could be the right endpoint or the left endpoint or middle or somewhere else, all right? Any point. And I am going to construct a rectangle whose height is the value of the function at this point. So this point here, I would call this x4 with a star, okay? So let me describe what I'm saying here. For each I, or for each subinterval, pick xi star, okay? And this is basically a representative. We are picking a representative from each subinterval, sort of like what we do in November in the election, right? You pick a representative from among those points on the interval, okay? Because your representative should represent your local, district, right? And so you pick X4 from the X4 star from the fourth subinterval, all right? And because representatives are stars, we put a star in here. That's not true. All right, pick xi star from from the ith subinterval, representative point. Okay, and number 3, of course the height of the ith rectangle. You see a bunch of rectangles now, right? The height of the ith rectangle is f of xi star, and the width, we already know what the width is, and that's delta xi, right? So we can see the area I, let area I, ai, to be f of xi star times delta xi, right? This is the area of the ith rectangle, right? See, you have to be really careful here because when we are trying to define this continuous version of addition, there is no such thing as continuous sum, right? So we have to start with some finite addition. And so we now have n things we are adding together. What n things? We are adding together, and I haven't done so yet, but we are adding together the n rectangular areas, right? So this is the next step here, right? And this is, as I said before, Riemann, a German mathematician who was well known for his geometric work. Riemann, who unfortunately, by the way, passed away at age 40 because of sickness. It's tragic death. He could have done a lot more, I am sure, if he had lived longer. But Riemann defined his sum, Riemann sum, as let's call this S, right? Sub n, because you have n subintervals that you defined. All right, so this is the sigma, of course, that's, and basically all this is saying is you add up the rectangular areas, you have n of them. So let's go from 1 to n, right? So this is the sum of all of these areas, right? And so this is called the Riemann sum. This is the total sum of the rectangular areas. All right, and so I'm sure you've seen this before because this is how you define a definite integral in the calculus. All right, but I want you to know, even at this point, and we're almost done with definition. And by the way, the definition of a definite integral is probably the longest definition you've ever seen in mathematics up to this point, because all of these have to be preset. Okay, I mean, everything I've mentioned here is part of the definition. You start with a partition, and then you define what the delta xi is. You pick a representative point, you construct these areas, the rectangular areas, and then you add up and write that sum as the Riemann sum. And finally, so let's say I have to have one more thing here. Let's call this what should we call this? The partition, let's call this P, okay? And we can define what the partition of P is, right? So this partition was randomly assigned, right? And these are randomly assigned points. It's just x of 1 has to be less than x of 2 and so on. And it has to cover all of these, all the interval from A to B. All right, so let the partition, this is actually the norm of P, to be the maximum of delta xi. Now, what are we talking about? Okay, it's a maximum length, okay, of the intervals, right? So this is called the norm of the partition, right? And we are going to let the norm of the partition go to 0. Now, what's wrong with saying let n go to infinity? Okay, well, you can let n go to infinity by just dividing the first one into much, much smaller pieces, right? I mean, n would increase if you just take one of them and make them smaller and smaller and refine the partition. But we don't want to do that. We want every one of these intervals to get smaller and smaller. Okay, that's why I want to get the maximum one to go to 0, because then every one of these intervals will go to 0. And of course, n would increase. Okay, n would increase tremendously. It'll go to infinity if the biggest of these subintervals goes to 0, right? So you take the limit of Sn, the Riemann sum, and so now you are going to have more and more numbers added, but it'll approach a limit if f is continuous, or if f is what we call integrable. If the limit exists, we call that function integrable. And so if this limit exists, okay, this is what we call the integral from a to b of fx dx, if it exists. Okay, so this is the careful definition of an integral of f from a to b. It is a limit. Okay, it's a limit of, it is the limit of this Riemann sum as the norm of the partition goes to 0. And if that limit exists, and I hope you have seen that these limits do exist for many functions f. And if this limit exists, we call that the definite integral. But notice again, it is a continuous version of addition. You're adding things, okay? And adding what? Adding a function value at every single point x between a and b. And of course, you can't add infinitely many points, okay? You can't add infinitely many numbers. And so we have to be careful here in saying that we are not adding a bunch of x values or a bunch of fx values. We are adding the areas of these rectangular pieces and taking the limit. All right, so that's the idea of that's really the answer to what in the world is a definite integral. Okay, so far we have only been talking about a function of one variable, all right? And so we are going to take a little break, and in the second part of this video, we are going multivariable, okay? We are going to add a variable and see how things go here. And remember, I talked about this Lego example. Right, this is a good one to remember. Think of the functions as stacks of Lego pieces, all right? And now if you have a function of two variables, x and y, this is what you will see, x and y, all right? And so when we come back from a little break in part 2, we will be talking about the integral for two-dimensional functions.